Hi, my name is Dana Golden. Doesn't look like anyone has showed up yet, but someone shows up, we'll just keep on rolling with that. Um, so today we're going to talk about linear algebra, optimization, and linear regression. Um, so linear algebra is at the heart of machine learning. It doesn't matter if you're doing the most complex tasks, like it doesn't matter if you're running a neural network or doing transformers, or if you're doing very simple machine learning tasks like linear regression. It is all based on linear algebra. The universe itself is fundamentally linear, which makes linear algebra incredibly useful for so many applications. And matrices are really at the heart of computer applications. There's a lot of things you can do with matrices. And with linear algebra, it's not just that linear algebra is important to machine learning, it's that machine learning tends to rely on a lot of very advanced linear algebra techniques. Why is optimization important? That's another thing we're going to discuss tonight. Most machine learning frameworks focus on optimization. As economists, we often try to view algorithms through the lens of optimization. Our agents and economic models are trying to optimize some objective function. Well, you can think of the machine learning algorithm as an agent in our model that's trying to optimize an objective function, and that objective function allows it to improve as an algorithm. So why are we reintroducing linear regression? This is a fair question. Econometrics is a background prerequisite for this course that almost all of you certainly have. So why go back over linear regression? First off, machine learning views linear regression in an optimization way that is a very useful framework if you're trying to do machine learning that I don't think you see a lot of in your principles of econometrics class. Also, linear regression provides a very good way through which to think about cost functions and provides a lens through which to see machine learning. This is a very basic algorithm, but it's an algorithm you can use to say, this is how these other algorithms work. And most undergraduate econometrics classes don't focus on matrix algebra. Matrix algebra is very important. It's useful to reintroduce linear regression in a way that brings in the matrix algebra. So let's start off with a simple review of matrix multiplication. So one thing that is very interesting about matrices as an element that you can multiply that is not the case for scalars or integers, or just really numbers, is that matrix multiplication is not commutative. So if you multiply if you have matrices A and B, and you create a third matrix, A times B equals C, B times A will not necessarily equal C, and it will also not necessarily exist. So matrix multiplication is not commutative, and the multiple of two matrices doesn't necessarily exist like they would in simple algebra. So to multiply two matrices, you multiply the first row by the first column, then you multiply the first row by the second column, then you multiply the first row, the third column. Second row, first column, second row, second column. So you'll get something that is A1, B1 plus A2, B4 plus A3, B7, and then commas, the second entry, A1, B2 plus A2, B5 plus A3, B8. And then you have the third entry, which is A1, B3 times plus A2, B6 plus A3, B9. And then the second row would be A4, B2 plus A5, B5 plus A6, B8. And then you'd have the third and the fourth. So let's review. You take this first row and multiply by the first column. And you take the first row, multiply by the second column until you have a fully created matrix. Now, something that's very important when you're thinking about linear algebra is the matrix dimensions. So matrices are M by N, where M is the number of rows and N is the number of columns. So you multiply an M by N matrix by an N by M matrix. So call matrix one, or sorry, row mat one needs to equal call mat two. So if you have two matrices and they don't have dimensions like this, you're not going to be able to multiply them. And when you multiply two matrices, you get something that has dimensions M by M in this case, or if you're multiplying two matrices M by K by matrix K by N, you would get something that was M by N. So really, these two dimensions go away, but it's very important that they be the same. And these two dimensions are left over. So something that's very important when you're running a machine learning algorithm is a lot of them rely on matrix multiplication. And pretty much every time you have to multiply two matrices, you need to make sure that the dimensions are the way you think they are. So you'll have to check, and we'll talk about how to do this in NumPy later today. You have to check that the dimensions are the same in the second dimension of the first matrix and in the first dimension of the second matrix. That's a very important thing, and it really is one of the most important ways to check whether you've done something right when you're creating a machine learning algorithm, particularly if you're doing it in TensorFlow or working with neural nets. A set of vectors vi from I equals 1 to n is linearly independent if the vector equation vx1 v1 dot 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 xn vn equals 0 only has the trivial solution x equals 0. So what linear independence means is that they're different lines. if two vectors are not linearly independent, they're effectively the same line. So why does linear independence matter? Well, if any of you have ever been working on Stata or maybe R, Python, and you've been running a regression, and you'll get the computer to complain, it says can't run the regression, it results in a singular matrix. That's why it matters. If two matrices are not linearly independent, if a matrix is not linearly independent, you can't invert it. So if a matrix is not linearly independent, you can't invert it, and so you can't solve the system. And also, you're going to have a row of zeros, meaning you'll have what's called a free variable if you try to solve the system. Furthermore, if two matrices are not linearly, if a matrix is not composed of linearly independent vectors, if a matrix is not composed of linearly independent vectors, they will cause other problems quite often. So you won't be able to row reduce without creating column zeros. You won't be able to invert it. You won't be able to take the determinant. Thankfully, a lot of the algorithms that we'll talk about even today and going on in the next weeks kind of help us tackle this problem of what happens if you have linear dependence in your vectors. Another important thing to think about with linear independence is this is why if you've ever told in econometrics, don't add the same number of dummies as your variable has categories. This is why, because you don't want to create a linearly dependent matrix that suddenly you can't invert, and now you've messed up your entire system. So now, are the following vectors linearly independent? I'll give a moment to you in chat to try and figure it out. So the vectors would be linearly independent if there's no combination of V1 times A plus V2 times B plus V3 times C that equals 0. So let's see. 2 times 1 is 2. So 4 times 1 is not 6. So we know that these two vectors are linearly independent. So we don't need to worry about those. 2 times 1/2 is 1. So 2 times negative 1/2 plus this would equal 0. And then negative 4 times negative 1/2 would equal 2. And that plus 5 would equal 7. So we know that this one and this one and this one and this one are linearly independent. I won't solve the entire thing, but actually these three vectors are linearly independent. All three of them are no combination of the three of them can result in an all or zeros. What's another way to check that? That's right. Yeah, you can check this by row reducing. So just because I think row reducing is probably one of the most important things to do in linear algebra. So let's row reduce. What we want is, for those of you who don't remember, we want a pivot in every row. And we can add and subtract. We can add and subtract columns and rows. And we can swap rows and columns. So a pivot means we want every row to have a 1, where that row is the first row in the matrix to have a 1. So we're just going to swap, and that row is and that column is with the first row to have a 1 is also the first column to have, or the first column to have that 1 in it, in the row. So we're going to swap this right here. So 1, 5, 0 to -4, 1, and then 2, 6, 0. And then we're going to make both of these zeros. And to do that, we're just going to subtract away. So 1, 5, 0, and then we're going to multiply 1 by -2, and that's going to be 0. Multiply 1 by -2, that's going to be 0. And then 5 times -2 is 10. 6 minus 10 is -4. 0 times -2 is 0. And then 5 times -2 is -10. So this becomes -14. This still becomes 0. All right. So now we have this. Oh, sorry, this becomes 1. This stays a 1. Now we have this, and now really this is great. We only need to make this we need to make the first entry in this column 0, and we need to make the third entry 0 in this case. So in this case, since there's only a -4 here, we can just multiply in the entire row. We can just multiply -4 by 5 over 4, and we get 0 here when we add them together. And we get 0, and we're going to divide this by -4, and we're going to get 1, 0. And we're just going to add 14 to the third row, and we get 0, 0. Because we have this is a 1, and then we're going to add that at 14 times row 2 to row 3, and we get 1. So because we could row reduce, and we actually, when we row reduce, we finally enough get the identity matrix. Because we could row reduce, which is a crucial thing to do in linear algebra. It's how you find determinants. It's how you it's one way to show linear independence. It's a way to get eigenvectors and inverses. Because we can row reduce, and we can get it to row reduced echelon form, look up row reduced echelon form, we know that the vectors are linearly independent. All right, now let's look at this one. All right, well, 2, 15, 3, 2 times 2 is 2 times -2 is 4. All right, so 2 times -2 is 4. So 4 minus 4 is 0. 15 times -2 is -30. 30 minus 30 is 0. Uh-oh. 3 times 6, 6 minus 6 equals 0. 3 times -2 is -6. Plus 6 is 0. So these vectors are not linearly independent. And in fact, when you try and row reduce this one, you can get, well, this we just showed you can make go to 0 by adding 2r1, -2r1 to r3. And then now you can divide this by 2, 1, 7.5, 1.5, and then 5, 7, 9. And we don't even need to go any further because we already have a row of zeros. So that shows that when you row reduce this, you should find out that it's not linearly independent. A matrix rank is the number of linearly independent rows. The rank of a matrix can be found by row reducing and finding the number of pivot points. So remember, a pivot point is in row reduced echelon form. It's the number of rows in row reduced echelon form that are not just zeros. This is a pivot because it's the first entry in the column, and it's also the first entry in the row. So that's good. This is a pivot. First entry in the column, first entry in the row. That's great. There's no pivot in this column. There's no pivot in this row. So that means that the matrix rank is 2. All right, the matrix rank is 2, and it's a 3-dimensional matrix. So that means it's not linearly independent and it's not invertible. So only square matrices are invertible, but in this case, the matrix is just not invertible because it is composed of vectors that are not linearly independent. So a square matrix's inverse is the matrix that when multiplied by that matrix is the identity. Well, most matrix multiplication is not commutative. Inverse multiplication is. Single matrices have no inverse. So in inverse, I want you to think of like Waluigi, Wario. Basically, it's a Mario character who is the opposite. The inverse undoes anything that the regular matrix does. It's crucial to all of econometrics to be able to find inverses. And an inverse allows you to multiply a matrix by its inverse and to get the identity. I will show in a moment why inverses are so nice. And so, like we show down here, a times a to the negative 1, a times its inverse is equal to a to the negative 1 times a. So that's a very useful property. There are a lot of useful econometric properties with inverses. In terms of finding an inverse, method 1, augment the matrix with an identity matrix and row reduce original matrix while applying steps to the augmented matrix. That's basically what you would do is you would take matrix A and you would draw a dashed line here, and then you would do the identity matrix. The identity matrix, of course, is 1, 0, 0, 0, 1, 0, 0, 0, 1. We row reduced to it earlier. It's the matrix that A times I equals A, I times A equals A. So it's the matrix that, when multiplied by another matrix, yields itself. You do A and I, you augment the matrix A with I, and then you row reduce matrix I, you get from A, you get to A row reduced, and then you get something else over here, B, B, and that is actually a to the negative 1. So that's one way to find an inverse. And then the other way to find an inverse is to multiply the inverse of the absolute value of the determinant. So you take the determinant and you multiply the inverse by the adjoint matrix, which is basically a mini matrix composed of determinants from around the matrix. If you ever need to do either of these techniques, look it up. You won't really need to much at all, because the point of this class is to show you how to do this in code rather than manually. By the way, one important note to make about inverses is that finding an inverse is computationally intensive, and it's not always possible. So when you're writing code, you have to think about, is this a scenario where it even makes sense to take an inverse? Matrix inverses can be used to solve a system of linear equations, crucial for econometrics and specific machine learning tasks. In principal component analysis, we'll talk a lot about these sorts of things. Determinants, another very important thing you can find in linear algebra. Really, linear algebra is about two things. One of them is the determinant. One of them is row reduction. Determinants have 4 properties. The determinant of the identity matrix is 1. Exchanging two rows multiplies the determinant by -1. Multiplying a row by any number multiplies the determinant by this number. And adding to a row a multiple of another row does not change the determinant. So a determinant is a feature of the matrix that provides a lot of information about the matrix and is very useful in performing operations on the matrix. Eigenvalues and eigenvectors. Eigenvectors are vectors that, when multiplied by a matrix, produce themselves times a constant. The constant is called the eigenvalue. Eigendecomposition is incredibly useful for principal component analysis. Eigendecomposition basically just entails finding the eigenvalue, which is the value at which the determinant of if you have a matrix A, B, C, D, the eigenvalue is the value at which A minus lambda B, C, D minus lambda has a determinant of 0. So if we're going to solve that, this is easy because it's a 2 by 2 matrix. We would do A minus lambda B, C, D minus lambda. And in order to find the determinant, we would do A minus lambda times D minus lambda minus C times B. So that allows us to find the determinant. And then we would solve that for 0, which, as all of you can see, is a quadratic equation. So you would just use the quadratic formula, or you would factor it. This is matrix projection. Basically, the errors of a linear regression are the projection of the projection of the data onto the y variable. A vector is said to be in space V if for scalar C A in V, and CA times A is in V, and for vector A in V, and vector B in V, A plus B is in V. So that's the important thing, is that spaces are self-containing, so you can't get out of a space unless you add another vector in another space. So if you have a vector that's in R2, you can't get out of R2. So you have a vector in R2. If you add another vector in R2, and a vector in R2 just looks like that. If you add another vector in R2, you're going to get a vector in R2. Same thing with if you multiply this by a scalar, that will just give another vector in R2. So the only way to escape a space is by adding in another vector that has a different dimension. So norms are the last really important topic we're going to talk about in linear algebra. They have 3 properties: subadditivity, which means that P of x plus y is less than P of x plus P of y for all x, y in x. Absolute homogeneity, P of Sx is equal to the absolute value of S times P of x. And positive definiteness, P of x equals 0 if x equals 0. So why are these useful? Why would we want to take a norm why would we want functions with these properties? So norms, you can think of them as a yardstick, as a measuring device. So one valuable norm is the L2 norm, which is the Euclidean norm, which is something you know very well from early on in your mathematical careers, which is just the regular distance. So Euclidean norm between A and B, points A and B, the distance between points A and B is A1 minus B1 squared plus A2 minus B2 squared plus A3 minus B3 squared, square root of all of that. So norms provide a useful way to think about measuring and distance. Importantly, this is huge in machine learning because you often have to deal with cost functions. And you need to think about how far away are you from the optimal result. And you figure that out by taking some sort of norm. So some examples of these, you have the Euclidean norm I just mentioned, which is just the distance between 2 points. Then you have the taxicab norm, which is the distance between 2 points, where instead of squaring the 2 points and adding up these squares and then taking the square root, you add up the absolute value of the points, and then you you take the sum. So taxicab is kind of like if I'm walking down here, I go down this street and I go down this street, and then this distance is the taxicab norm, but the crow that's flying would just go this way, would minimize in this direction, which would yield the Euclidean norm. So the L1 norm will often yield different. So if you use these as cost functions, which you normally will, the norm you choose has dramatic effects on the outcome of your optimization procedure. If you use the Euclidean norm, you're doing something very particular in econometrics called minimizing the sum of squared errors. So the Euclidean norm is a cost function we economists are very familiar with. The taxicab norm, interestingly enough, does not minimize the sum of squared errors, but whereas the Euclidean norm finds a conditional mean, so that's why economists like it, is because it finds the average conditional on your data. The taxicab norm finds the Euclidean median, or not the Euclidean median, conditional median, sorry. So analytical optimization. One other thing I want to mention is that norms can never be negative. Norms are always positive or zero. So you can't have negative distance. It just doesn't make sense. You can't have a negative weight, as much as I'm sure we all wish we did. Analytic optimization is the most well-known to economists. It involves finding the maximum or minimum of a convex function, and it can be done only for functions with analytic maximums or minimums. You can use this. You use this technique very often in your intermediate classes. In intermediate macro or micro, you're often going to be told, find the optimum of this function with respect to these constraints, maximize this happiness. In the real world, you often can't do that because in the real world, most functions don't have analytic maximums. You can't just take a derivative and find the maximum or minimum. You have to solve for it because most functions in economics we deal with a lot of nice functions that generally are convex. And convexity is a really great property when you're maximizing a function. If you have a convex function, it looks like this. And if you find a local maximum or a local minimum, you found a global maximum or minimum. So convexity has really nice properties for optimization. On the other hand, most functions don't have convexity as a property, so you have to find ways to optimize them when instead of looking like this, they look like this. So how do you optimize poorly behaved functions? You do it through a technique called gradient descent. And that's how you optimize functions in the real world, is you take steps down, down, down this hill, you find the derivative, and you take steps down, down, down this hill until you get to the bottom. So you're rolling a ball, and the ball rolls a little bit, and you make sure that you're still going down. It rolls a little bit more. You make sure you're still going down. Rolls a little bit more. You make sure you're still going down. Rolls a little bit more. Maybe it rolls a little bit over here. Now you take the derivative, which is the direction the ball needs to go in. It goes a little bit over again, goes down, and eventually it ends up there. So gradient descent is a technique for finding the optimum of a function by moving small steps in the direction of the gradient, which is also the derivative. Stochastic gradient descent is performed by taking gradient from one random observation I and taking a step in that direction. So if you'll notice, gradient descent kind of uniformly moves towards the objective. Maybe it overshoots it sometimes, but it basically goes in the direction it wants to pretty much homogeneously. Stochastic gradient descent, though, goes up here, goes down there, up here, down there, up here, down there. It doesn't really go in any nice direction. So this is a lot computationally faster in many scenarios, not always computationally faster, but it is a lot more haphazard and can go in random directions that you wouldn't expect. Most machine learning algorithms utilize stochastic gradient descent because it is a lot faster for most things machine learning people want to do. Newton's method is another method you can use. It basically, in gradient descent and stochastic gradient descent, we have this alpha. And this alpha we leave constant, and basically it tells us how quickly to walk down the hill. But, there's no reason why alpha should remain constant. Maybe we want alpha to change over time. How should we even choose alpha? That's a really important question. Newton's method finds the optimum of a function by choosing alpha to be 1 over the second derivative. So it scales the rate at which the function you're moving down the derivative based on the second derivative. So if you'll notice, if the second derivative is decreasing in magnitude, you want to get smaller, or the second derivative is increasing in magnitude, you want to get smaller and smaller adjustments to in Newton's method. So that's just an important feature of optimization. So now let's derive least squares linear regression using matrices. We have y equals beta x plus u. And remember that least squares linear regression minimizes the sum of squared errors, which minimizes y minus beta x squared. So we want to find the beta that minimizes the sum of squared errors. And so to do that, what we want to do is we want to take the derivative, take the matrix derivative, and the matrix derivative is the same as you take a regular derivative, except now you have this squared is y minus x beta times y minus x beta, which is y squared minus x beta y minus or plus x times x prime x times beta squared. And if you take the derivative of that with respect to beta, this goes away because there's no beta. This beta goes away, so it becomes negative x y, and then x prime, or negative x prime y, negative x prime y, and it becomes xx, and then not times beta, times 2xx times beta, and then if you take the matrix derivative, you get x prime y minus x beta equals 0. And then we need to solve that for beta. We get x prime y minus x prime x beta equals 0. X prime y equals x prime x beta hat. Beta hat is, of course, an estimator. That's a very important in economics to distinguish between an estimator and just a true value. So the true value is beta, and then the estimator is beta hat. Beta hat equals x prime x to -1. So that's where we're taking the inverse. Remember we talked about inverses earlier, times x prime y. Least square is asymptotics. If we want to find the expected value of beta hat, because functions converge to their asymptotics, we find the expected value of x prime x to the -1 x prime y, which is, that's our value for beta. So we need to find the expected value of x prime x to the -1 x prime y. And so we can sub in here. We know that y is equal to x beta plus u. And so we can sub that in there, and we multiply x prime x to the -1 x prime x beta, and then plus x prime x to the -1 x prime u. So x prime x to the -1 times x prime x. This all goes away because x prime x is the inverse. X prime x to the -1 is the inverse of x prime x. So that just equals identity. So this becomes beta. And then we're left with beta plus x prime x, x prime u, and this asymptotically goes to 0, which leaves us, if this asymptotically, if this term right here asymptotically goes to 0, this leaves us with the expectation of beta asymptotically converges to beta. So why does x prime x to the negative 1, x prime u go to 0 asymptotically? Why is the expectation of that 0? I'll give you time to think about it. It's because the expectation of ax is equal to the expectation of equals a times the expectation of x, because a is a constant. This is actually a constant here. It's not changing. So this becomes expectation of, or this becomes x prime x to the negative 1 x prime to the x times expectation of u. And the expectation of u is by assumption 0. There are econometric models in which it's not 0, but in this case, it is by assumption 0. So that's some stuff about the expectation of least squares. Now, does the error go to 0 though? No. In this case, you can find the error. You can find the standard error, which is the variance, by doing expected value of beta hat minus expected value of beta hat times beta hat minus expected value beta hat. And then beta minus expected value of beta hat is x prime x to the negative 1 x prime y. So beta minus e of beta hat is, this is the expected value of beta hat. So it's beta minus x prime x to the negative 1 x prime u minus beta, let me fix that real quick. Beta minus beta plus x prime x to negative 1 x prime u. And that's equal to this beta, and this beta goes away. So that's equal to x prime x, x prime u. And then you multiply that together with itself, and you get x prime x to the negative 1, x prime u, u prime, x prime x, x prime x to the negative 1. So everything in this equation is a constant except u. So and the expectation of u is 0, but the expectation of u times u prime is sigma squared by the assumption of homoscedasticity. So the variance of our least squares linear regression estimator is sigma squared x prime x to the negative 1. What happens if the x values are correlated with the error term? Then expected value of beta hat is equal to this still, but now this does not go to beta because x times u, x prime u, does not equal 0. In fact, this goes off towards infinity. Does anyone know what this situation is called? That's right. This is called the endogeneity problem. So when x is correlated with u, you don't necessarily get to count on the expected value of your estimator being correct. What happens if the y values are correlated with the error term? Does anyone know? That's right. Nothing happens. It's totally fine for the y values. to be correlated with the error term in terms of the expectation of beta hat, you only have a problem because you have the problem of heteroscedasticity. You only have a problem with the variance. So you need to find a way to fix your standard errors, but the expectation of beta hat will still equal the expectation of beta if you have y values that are correlated with the error term. So now we have our way of finding least squares by linear algebra. So linear algebra is incredibly important in machine learning. But now let's talk about how to derive least squares from maximum likelihood. So notice that it still has this expected value of 0, but it also has an assumed distribution, which is IID normal 0, sigma squared. So the likelihood function is just a series of normal. The likelihood function of linear regression is just a series of adding up the likelihood function, multiplying the likelihood function of a series of normal random variables. And the product of a series of normal random variables, nice little fact of the normal distribution, the product of a series of normal random variables is normal. So we have, this is the likelihood function of a series of normal random variables. And then if we take the logarithm of this, as we normally do when finding the maximum likelihood, we get something where the first term does not depend on beta. Second term does not depend on beta. Only the third term depends on beta. If you'll notice, taking that derivative and maximizing it is the same as maximizing, or finding the derivative of that and then z equals 0 is the same as minimizing the sum of squared errors. So maximum likelihood estimator here gives the same estimator as the analytical estimator in least squares, which is not always the case. So that's how you use maximum likelihood on least squares. So algorithm computationally for solving least squares using maximum likelihood, start with the cost function, minimize and minimize. So start with the cost function, minimize the cost function by taking the gradient and stepping towards the gradient. How do you find the standard error? This is a great question. This is very important. Basically, you find the second derivative matrix, which is the Hessian matrix, the information matrix, and that will allow you to find the standard error. You can also do it through Monte Carlo, which is not something we'll get into in this class, but it's important to know. Cost function is a function you attempt to minimize within machine learning context. Like I said before, it's often a norm. It's how you measure how well your algorithm performed, mean squared error, log loss. Generally, you make log loss negative. Why? Because you want to maximize log loss rather than, you want to maximize log loss rather than minimizing log loss. It's easier to maximize something than to minimize it. So finally, we'll talk about several different takes on linear regression from the machine learning world. The first one is lasso. So basically, all that lasso is that you do a technique called regularization, is what I'm about to show you all of these, and you use the L1 norm. So L1 norm is a taxicab norm. It's summing up absolute values, and you sum up the absolute values of your betas. So what lasso does is it chooses the variables that improve the data set. So it's used to choose variables and prevent overfitting by choosing a minimum of a function that minimizes the minimizes the sum of squared errors subject to the L1 norm of the betas. So this sometimes will make this is a way to automatically adjust your coefficients, automatically choose coefficients, and we'll set some of your coefficients to 0. So we'll choose the coefficients that should be greater than 0, and it will regularize your data to prevent what's called the overfitting problem. So ridge is the same thing as lasso, except you use the L2 norm. And it scales all coefficients based on their value for prediction. And it can perform regression even when collinearity exists. So whereas lasso finds the coefficient that should be 0 when you are regularizing, ridge is basically lasso, but it finds it scales the coefficients based on how valuable they are to the regression. So this is valuable compared to lasso because it has an analytical solution that can be performed even when collinearity exists. ElasticNet uses both L1 and L2 norms, and it's a compromise between lasso and ridge. So this is a visualization of ElasticNet, lasso, and ridge. And the coefficients you get from each of them. ElasticNet is kind of a go-between between the two. Yeah. Thank you so much. This concludes the first PowerPoint. Now I'm going to go back to the PowerPoint from last week. I'm going to talk about NumPy. So NumPy is an incredibly important tool in machine learning. It allows you to work with matrices and large data sets in Python. NumPy dramatically speeds up Python operations through a technique called vectorization. NumPy is effectively MATLAB in Python. It's extremely valuable for econometrics and machine learning. And arrays the unit of observation in NumPy, arrays in matrices. By creating arrays, we can perform NumPy operations. To create arrays, np.zeros creates a matrix of specified size of zeros. np.ones creates a matrix of specified size of all ones. np.linspace returns evenly spaced numbers over an interval using the count, the number of numbers you want between two values. np.arrange is same as linspace, but it uses step size. So instead of using the count, it returns evenly spaced numbers of a certain step size. np.I creates an identity matrix of a certain size. Array.shape gets the dimensions of a shape as a tuple. Len of array gets the length of an array. So if we have an array A and an array B, we can subtract them, we can add them, divide them, and we can multiply them. Notice A times B is not the matrix product of A and B. It is actually the element-wise product. So you're multiplying, instead of multiplying like we talked about earlier, multiply this times this. Or sorry, you multiply this times this, 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 this times this. So it's the element-wise product rather than the matrix products. Other matrix math, np.x finds the power of e to every matrix element. np.log takes the natural log of elements in the array. np.square root takes the square root. np.sign gets the sign, and array.dot array2 gets the dot product. Matrix operations, at multiplies two matrices, time find the element-wise multiplication. Dot t takes the transpose. Linealge dot eigenvalue takes the eigenvalues and eigenvectors of an array. Linealge dot inverse computes the inverse, and linealge dot norm computes the norm of a vector matrix. So Boolean masking is an important technique in basically all of Python when working with arrays, and allows you to pull from NumPy array based on certain conditions. So you have an array of true, false, false, true, and then you have source array and then destination array. And then you get where it's true from the source array. So true here, 65, 65. And then you get where it's false from the destination array. So this allows you to only pull the elements that fit a certain criteria. It's very important in Python. So linear regression is using matrices in MATLAB or in NumPy. Beta equals x prime x negative 1 x prime y, as we talked about earlier. And then in NumPy, you can either do x dot transpose at x dot transpose at y, or you do np dot linearalg dot least squares x and y. So that is NumPy. Now I'm going to stop sharing for a moment, and I'm going to go to my code. And we are just going to look at some code together for matrix calculus. So we're going to start off by just loading our packages. Then we're just going to take some standard dot products. So you can take the dot product and just multiply two numbers. You can take the dot product and multiply two matrices as dot products. You can also create some arrays. So this is using a range. I encourage you, even if you're not like here presently with me, I encourage you to follow the home game and be working on these codes alongside me. So np.ones, it creates a matrix of ones of a set size. np.0 is also just going to create a vector of zeros, but we can also create it of other sizes. So these will create 5 by 5 matrices of ones and zeros. And np.I, which is identity, will create a 5 by 5 matrix of 1 on the diagonal. You can also create matrices that have more than 2 dimensions. So you can create matrices with as many dimensions as we really want. We can initialize a matrix with dimensions 5 and 5 of just zeros, and we can add 5 to it. And what do we get? We get a matrix of all 5s. We can also do the same thing if we wanted to by adding 4 to a matrix of 1s or multiplying a matrix of 1s by 5. Let's create a linspace. We can also, so we can create a linspace. And then if we want to get the dimensions, like I was talking about earlier, it's very important to get the dimensions sometimes. We can do abc.shape. So dot shape gives us the dimensions of an array. We can also index. So b of 0, 0 will get the 0, 0th element of the array. In this one, 0 column or 0 row, that's this one. And then 0 column, that's this one, 4. So it should give us 4, and that it does. This one, you have the colon in the first, and then the one right here. Remember, Python indexes from 0. So it's going to get at us the second column of B. And that's exactly what it does. Second column is 1, 2. And that is exactly what it does. So this gets us objects 1 to 2 in the matrix and 0. It actually only gets us one object because there's only 2 rows in the matrix. This code shows us how to transpose some matrices. You can do np dot transpose, or you can do dot t. These are some simple element-wise operations: a minus a plus b, a minus b, a plus c, a plus v. Oh, what? We can subtract v from a. Why can't we can't add a and b? Why can't we do that? Why not? It's because a and v don't have the same dimensions. So you can only add two matrices together if you can cast them on each other. And so you can actually add together A and C because C is actually not itself a matrix. It's a list of matrices. But you can't add together A and V because V is just a vector of a different shape than A. So it's very important to make sure that you're thinking about your shapes when you're doing this. You can also multiply matrices. In this case, we're using matmul. And there are some matrices multiplied. You can also do this, where you multiply a list of matrices. This multiplied a list of matrices by matrix. And then A times B, notice, is not the same thing as A is A dot B. Notice these are two very different operations. One is element-wise, one is the matrix product. You can also convert the type of a matrix. So this will force 2.5 down to 2. And you can get the rank of a matrix. So we talked about matrix rank before. So the rank of this matrix is 2. This is, if you'll recall, linearly independent. And then the matrix of a matrix of all ones is just 1, regardless of the size of it. And then the rank of a matrix of all zeros is, of course, 0. The trace, or the number of pivots of the identity matrix, is the number of rows in the identity matrix. You can also invert matrices in Python. Made an error here. So how did we do? We need to do np.linalg.inverse. All right. So always important to remember that sometimes you make errors and you need to figure out what is going on there. There's nothing wrong with making an error when you're coding. It's just important that you be able to figure out and fix it. You'd also take determinants in NumPy. So here is the determinant of that matrix. Actually, this is a set of matrices. This is a list of matrices. You can solve a linear system. And you can do eigen decomposition in NumPy. So we can find the eigenvalues of a matrix, which is an important thing to do in just math generally. You can also raise a matrix to a power. Here I'm going to raise this matrix I to the power of 3, and then the power of 0. Notice the matrix to the power of 0 is just the identity matrix. You can do Cholesky decomposition. Look into that if you're interested. And you can create random matrices. This is something you have to do all the time in machine learning, is create random matrices. This creates a random matrix of that size. So let's see what it looks like. So it looks like that. This will create the same, but will create a uniform random matrix based on, look at how this one, it goes over 1 and 0. This creates a uniform matrix between 1 and -1. So all the values are, between 0 and 1. So all the values are between 0 and 1. This one here, we can also create a normal random variable to create a matrix. So let's create a normal random variables matrix. And then we can create a histogram showing that it is normal. So there's a histogram showing the normalcy of our matrix. You can also set the random seed. You set a seed so you get the same values when you run the code again. If you set different seeds, you don't necessarily get the same value when you run the code the next time. You can perform random sampling, and you can perform shuffling in NumPy, which basically shifts the element in your matrix. It creates a random new order for your matrix. Here are those basic mathematical operations applied to our random matrix. And here are some basic statistical operations. You can also provide, you can sum. If you sum by the first axis, you're summing by rows. If you sum by the 0 axis, you're summing by columns. And then, yeah. Notice that NumPy does not have the object median. It only has mean, but there are ways to take a median of a NumPy matrix. It's just not by that. Here's how you perform QR decomposition. And then you can also take a norm in NumPy, and all you have to do to take a norm is just have the matrix and then the type of norm you want to take. So you can take the negative norms, you can take up to norm np.inf. So the infinity norm is basically if you know what an infinitum or a supremum is, the infinity norm is the supremum of the norms. And then you can also perform singular value decomposition. Singular value decomposition, we'll talk about it, I believe, next week, is a very important concept in principal component analysis. This is perform singular value decomposition. You can also stack and split vectors. And then you can perform linear regression with NumPy, perform linear regression, and then we'll create a plot of our linear regression. And then, yeah. So that was a quick introduction to NumPy. If you have any questions, please email them to me, or I'll be more than willing to answer any questions you have. So now I'm going to do an introduction to linear regression and lasso and ridge. So first off, we're going to import our packages. So I've installed sklearn since last week because I realized I did not have that installed. So install sklearn. If you have any trouble installing packages, always happy to answer. Hit me up during office hours, just anytime. And then this code, all it does is it finds the analytical linear regression solution. So let's go through it. Create a y vector, you create an x vector, or you create an x vector, you create a y vector, and then you concatenate the x vector with an np.1. So you have a invert or an intercept, and then you take the inverse of x augmented transpose at time, multiply that times x augmented times x augmented transpose times y, and then you get your beta analytic. You can also do this through gradient descent. So here, basically what we're doing is we're finding the error, we're finding the derivative of the function with respect to the error, forming the update step, theta minus alpha times gradient. We're finding the cost function, we're getting the cost function again, and then we're just forming the linear regression. To form the linear regression, we get the augmented x, we augment the x with the ones. We initialize just a random theta of the same shape as x, and then we perform gradient descent. We're going to choose an alpha of 0.01, and we're going to choose 1,000 iterations. So let's see what happens. All right, so cost function could converge really quickly. So the cost function converges really quickly as we expected it to happen. In linear regression, that's great. That means that your work gets done really quickly. And then let's plot our gradient descent linear regression versus our original linear regression. Slightly different fit, but very, very similar. So yeah, this is, this is our linear regression versus the original data, I should say. Linear regression versus our original data. And that is linear regression with gradient descent. We can also perform lasso and ridge. So lasso, we get the shape of our data. We initialize a random matrix for beta. We basically perform linear gradient descent again. But now the important part is when we perform gradient descent, we add in this lambda to our cost function. And when we add in this lambda, we are regularizing it. We're penalizing it for having a larger coefficient, and we're setting some coefficients equal to 0. So in this case, we have different coefficients than we would have otherwise. And we are, if coefficients of ours don't matter, we would set them equal to 0. Ridge, as I said earlier, can be solved analytically, or it can be solved through gradient descent. So this is the analytic solution. You just inverting with the added lambda. So you just can solve for your betas through that analytic solution. I know it's something that looks like the solution from Lasso, only it will have scaled coefficients versus the coefficients in Lasso, which are some of which will be 0. The more we're choosing coefficients rather than scaling them. And then this is that, but now from gradient descent. So now instead of analytically solving, we're solving through we're solving the for coefficients using the technique of gradient descent. And then elastic gnat is an in-between between bridge and lasso, where we have a lambda 2 and a lambda 1. A lambda 2 is multiplied by the square of beta, and a lambda 1, and that's mirrors ridge, and a lambda 1 is multiplied by beta, so that mirrors, or the absolute value of beta, and that mirrors lasso. And we can also get the betas there. So that's how you would get that's how you would do ridge, elastic gnat, lasso, and linear regression in Python. You can also do them using sklearn. So basically, sklearn, what's really cool is it implements the implements the algorithm for learning for you. So we just initialize our learner, and then we do fit, and then we do predict. So initialize learner, fit, predict, and then we get our coefficients. And we also get ypred, which is our prediction of y. So if we want to get our errors, we would do y underscore pred minus y. and these are errors. They're minimized, which is why they're relatively small in this case. And we can also do lasso in the same thing. Just do lasso. We initialize our error with our parameters. Our parameter here is alpha equals 0.1. We fit it, and then we predict x. And then we get our intercept. We get our coefficients. And then we can do y pred lasso minus y. And those are errors. They're a little bit larger in this case. They're not always going to be larger. I will say they are usually larger on your training data because lasso is regularization. So the idea of like regularization is to stop overfitting. So you want the errors to be larger in your training data, but smaller on your test data. And you can also do the same with ridge and with elastic net. So now notice how much easier this is. sklearn has taken the hard part out of it, and we just have the you just have the learner as a function. So yeah, that's lasso, ridge, elastic net, and linear regression in Python. That's how you do it using NumPy. Let's talk a little bit about optimization, and then I'll let you go. So this is gradient descent for a simple quadratic function. So it's a very simple function, so it should be very efficient on there. So let's see how it does. So it is minimizing the quadratic function. If you'll notice, I believe the minimum is -2. It doesn't look like it hits there here, but basically is taking smaller and smaller steps away from a starting value towards -2, and it gets really, really close to -2 in these 100 iterations. Let's say we make it 10,000 iterations. Let's see how close it gets. So it gets really, really close. It's effectively equal to -2. As close as we're going to get with linear regression or with gradient descent. Now we can also perform Newton's method for a simple quadratic function. One thing I want you to notice about what we just did is that we didn't get the exact solution. We got really close to the exact solution. We didn't get the exact solution. That's something you're going to find in gradient descent is you're going to find that you're not always going to get the exact solution, but you're going to get very close to it. So we have a simple quadratic function. So the second derivative of this quadratic function is 2. This is the same as this one up here, by the way, up here. So if we take the first derivative, it's 2x plus 4, and the second derivative is just 2. So this is Newton's method with a simple quadratic function. We take the gradient, which is at 2x plus 4, and then we divide by the second derivative, and we'll get something very similar to in gradient descent. So let's see what happens. So here we go. We get -2 as our optimization termination, and the optimization terminated successfully. And so I have a little bit more in this code about how to do this for logistic regression. We're going to make you do that on your homework. So I think I'm just going to leave that up to you to think about later. You can also do the same thing with SciPy with constraints like we do here. And that will do effectively the same thing. And you can do differential evolution to also find the minimum. And then finally, I've written up some code that you can look at here. This is an application of optimization, uh, and this basically solves rock paper scissors for the optimal strategy using linear programming. So it's a really fun thing I think you should look at. If you're into game theory, this is how you apply game theory in Python. And it finds a linear program that basically enforces that classic game theory rule, which is no strategy. You should put in place the strategy because rock paper scissors is a minimum is a zero sum game. You should do the strategy that tries to screw over your opponent. So take a look at that. That's fun for any of you game theorists. I also have some. I have this optimization ML4T, which is some optimization with respect to trading. So if you're interested in machine learning for trading, I have some trading code I have written throughout the course that I'm willing to show if anyone's too interested in it. And then I have some other examples if any of you are interested in that as well. Finally, in terms of the exam, please email me if you have any questions. Please also attend office hours if you can. I'm always responsive to emails. I think there'll be a practice exam, and that'll be out soon. But yeah, really prepare, study. It'll pretty much all be over things before optimization, and do a great job. I hope you all have a great day.